Hi, so this is a continuation from the last video. This is, if you remember, the Linear Technologies current sense amplifier. We're passing a current through a 0.02 ohm resistor, measuring the voltage, amplifying it by 50 times, and then what I've got the varying voltage running into a Pic microcontroller. Doesn't matter which one, but this particular one's the 32-bit. Forget all the ribbon cable. I've disconnected my 5-inch screen, just got the regular 3.1-inch TFT on it. I'm running two analog to digital converters. First one's measuring milliamps from the Linear Technologies current sense amplifier. I've then got 3.2 volts running to the amplifier board, and then we're using Ohm's law, multiplying the current by the voltage, or voltage by current, doesn't matter, and giving us the milliwatts output. So if I give you a quick refresh, so I'm using, that's the power supply, and that's 3.3 volts. On the right is feeding the Linear Technologies amplifier, and then the left hand one I'm just winding up through a 50 ohm 5 watt resistor to give us our varying current, which you'll see on the bottom. So turn it back down to nothing, and there's the meter. It's measuring the output from the amplifier. I'll show you the code. Hopefully you won't need the schematic for the amplifier because it's on the previous section. Right, so if I start turning the voltage up, which is going through the current sense resistor, we'll start measuring the output of the current sense amplifier. So you can see 0.045 volts, and you'll see the current. It's not 100% accurate. I think Linear Technologies quote 1% tolerance, but then you've got my resistors taken into account, which are less than 1%, but it's close enough for what I need. Right, so you can see we've got 100 millivolts coming off the amplifier. That's running into the Pic microcontroller, being converted, and we've got 105 milliamps. In fact, you can see, so don't forget, when we're doing the analog to digital conversion, we've got 1024 steps, so it's breaking that voltage up 1024 steps. So you see it will go step up or down from the previous voltage or the next voltage, or in this case the current conversion. This is obviously the 3258 millivolts going in for the linear amplifier, and then I'm multiplying that by that to give us the milliwatts. I've got the meter there so you can check the accuracy of the amplifier. So if you look there, 303, I saw 2 there, 2.5. So that's the output, nice and steady from the linear amplifier. .366, so it's still plus or minus 1, but what I've actually done on the code, I'll show you how it's done, broken this down to the values coming in, and I've actually added 5 or 6 to the result, and then depending if it's over or under a certain level, it takes it 5 or 6 away, or adds or subtracts 2 from the result, just to give us a better calibration. And you see, as we increase the current, voltage is remaining the same, and obviously the milliwatts are increasing, so 1677 milliwatts, or 1.6 watts. Right, so that's 31 volts on my power supply going through a 47 ohm 5 watt resistor. So we now got 2 watts of heat in a 5 watt resistor, so that's now going to start to get hot and eventually it will melt the solder. But this power supply through this resistor and in fact we've just melted the wire off the resistor. I put this braid on the resistor just to keep it away from the board, stop the resistor heating up the current sensor resistor. Turn the light on, you might be able to see it. And so that 2 watts of heat we just had, 2 watts of energy, it's been heating this up, and that's melted that. I'll use some solder braid because it's all I had to hand, couldn't be bothered to go and get a piece of wire. Right, so you saw that working, you saw it's accurate, the amplifier was nice and linear. Now I'll take you to the screen and show you how to do the code for the 2 analog to digital converters. Right, so this is the code. As always, this is the configuration for the TFT. If you're using microelectronics MikroC, use the built-in H. Right, so that's the TFT display. That's the initialization for the TFT, or the specific type of T that I have. Right, these are the basics you need for the code. So I've got an unsigned int, milliwatts, unsigned int for the first ADC converter, so that's for the current on port B0. I'll show you more about this float in a minute, but it can be an unsigned int or float, ADC underscore value 2. That's just what I've called them. You can call them anything else, or anything you want. You can call that unsigned int voltage, unsigned int current. But because it's the analog to digital converter, value 1, value 2. So then these chars underneath, so that we can display the result on the TFT screen. I've got 12 places here because when I change it to an int we need more spaces here, and then the char for the milliwatts text so we can display the milliwatts on the screen. Down to the main, so initialize touch panel. Right, this AD1 PCFG, that's a configuration for the setting the pins to analog or digital. So I couldn't find it on Microelectronica. Have a look at the data sheet. The data sheet then tells you to look at section 17, which I'll bring up here. Section 17, 10-bit analog to digital converter, ADC. So if we flick down to page 4, so down at the bottom of page 4, here's our AD1 PCFG register, bit 0 to 15. They relate to our 16 analog to digital pins we've got on this particular Pic. So although it says 15, remember 0 is a number, so 0 to 15 adds up to 16 channels. So how do you relate that to the pins you're on? So if I go back to the code, so if you look AD1 PCFG, so we got, this is hexadecimal OX, FF7E. So I'll show you a quick way of doing it. If you've seen any of my other videos, you'll be familiar with this method. So I want channel 0, which is B0, and I picked for the millivolts, I picked channel 7, just so we can see the difference, see what we're doing. Instead of 1 and 2, or 0 and 1, I picked 0 and 7. So pin 0 of B and pin 7 of the B port. So bring up the calculator, Windows calculator, change the configuration view to programmer. We want pin 7 and pin 0 as analog and the rest digital. So here select binary. So look, 15, 14, 13, 12, 11, 10, 9, 8, 7 is analog, 6, 5, 4, 3, 2, 1, back to digital, and then 0. is analog. So that's our binary representation of how to configure this port. So you could, on the register when you're writing your code, put 0B for a binary representation, or just convert it to hex here, FF7E. Which is what we've got there. Right, what I'll do to prove this binary to hex conversion, so you see we're setting the various pins, or 2 of them to analog, the rest digital, and you see there I've written a small note on the screen. If I can scroll it across, so B0 and 7 analog, page 4, section 17, 10-bit analog to digital converter. So what I'll do on this calculator, you can actually go back to get you in view, go back to binary, and you can look, right click, copy, minimize that. Right, let's shift all this out of the way. Get that out of the way, put 2 slashes there to remove that statement, right click, paste. Right, that's our binary representation of the ports we want to for analog and digital. So that's now binary, so we put a 0B and then a semicolon. Right, this is a JTAG, disable, Tris A, as you saw from the other video. You might remember the value of the current is also being represented on port A in hexadecimal form. Well, I've just noticed this was from when I was first messing around with the current. So Tris B0 underscore bit is 1, so port B0 is an input. I've just realised I've been using Tris B .7 as an input as well, and it's not configured here, so I'm presuming this and a MikroC compiler must do it for me. So what that should be, in case you're having trouble with your code, in fact, if I look, just right click, copy, paste, and we want bit 7. Right, this is the analog to digital conversion channel initialization, and Microelectronica tell you that once you initialize the ADC, it does everything else for you. It sets up the internal clock as the sampling, sets the voltage reference to internal VSS and VDD, which if I scroll down a page, done by these 3 bits here, VCFG, bit 0, 1 and 2. So that's the internal VSS and VDD. Back to the data sheet, page 8. Right, you can see there, messing about with these configurations, you can use an external reference, which Microchip actually advise under certain conditions. They say if you've got an external reference with a precision voltage reference IC, you can get better sampling. Depends what the Pic is already doing, but in certain applications it might be advisable to use an external reference, either positive, negative or both. So messing about with those 3 bits determines if you use an internal or external reference. Close that down. Right, now we're onto our while loop. So it's the same as the other day. We're looking at the sample on the first converter, which is the current conversion, and we're latching the port, we're latching the pins in port A to the value of the current in milliamps. So depending on what the current is, different LEDs come on, give you a hexadecimal representation of that value. Then ADC value equals ADC value get sample from pin 0, and then this is a second ADC converter for the voltage. So ADC value 2 is ADC 1 get sample 7, or you can say ADC 1 read, but this get sample is meant to be quicker. So then this conversion here, we've got the value of the ADC result. So the value of the ADC equals the value of the ADC times 3.222656. Now how do we come by that figure? Get the calculator again. Right, on standard view. So our supply, the VSS and VDD on this particular PIC, it's a 32-bit PIC, so they use a 3.3 volt supply, something like 2.7 up to 3.6 volts. This particular PIC is running at 3.3 on EasyPIC's Fusion version 7 board, so we want 3.3 volts divided by 1024, which is our 10-bit, equals 0.0032. So we are going to get, if you look at this first three, so that there's hundreds of milliamps or millivolts, tens of millivolts, and then just units of millivolts. So look, 3.22265625 millivolts. So look, 3 millivolts per count. So 1024 of those counts will bring us up to 3.3 volts, which is our supply rail. So depending on what PIC you're using, if you're using a 5 volt PIC, then you want to divide the supply rail. So like 5 volts divided by 1024 equals, obviously we've gone up by a millivolt, we've got 4.88 millivolts, or 0.004 volts. That's how I've come to that figure. But what I've done to give us the answer in millivolts, I've moved the decimal place. So instead of it being 003 blah blah blah, I've moved the decimal place to here. So it's gone up by 1,000. And you'll remember from Still Flash Boy over there, we got 3,254 millivolts. And similarly with the second capture, that's for current, this one's for the millivolts, just measuring literally the millivolts on the linear regulator, linear amplifier. So we've got the same again. And then there's a conversion using Ohm's law, amps times volts. So what we've actually got, so because we're using milliwatts, so it's the ADC value, which is actually milliwatts, times the second ADC value, which is millivolts, but you see it on the screen, it's 3,250 millivolts, so we're actually dividing the second value by 1,000. This is effectively milliamps times millivolts, gives us milliwatts. Now this is the calibration I was talking about. If the ADC value is greater than 1, ADC value equals ADC value plus 6. I found that gave me a good calibration for up to about 400 millivolts, milliamps. If the ADC value is greater than 408, ADC value equals ADC value minus 2. You remember from the meter we were plus or minus 1 or 2 millivolts, milliamps, depending on if you're looking at the display or the voltage coming in. But finally, this is just our text for the screen. So that's just random text in black. So int to string for our first value, which is the current milliamps, TFT write text for ADC result text, interstring for the millivolts, and then interstring milliwatts text. That's a milliwatts, and we're writing the milliwatts down here. Then we're pausing for 1/10 of a second and writing the same again in yellow, so that's just clearing the number and writing it in yellow, which is why you saw the screen flashing black and yellow. Right, so I've changed the second ADC to a float. I've also gone back up here and moved the decimal place. Do you remember it was 3.22? So I've moved it 3 places. 1, 2, 3. So this is our sample coming in. Do you remember we divided the supply rail by 1024? And that's the result on the calculator. So that's our ADC value. That's the real value coming in. So real value times that number coming in gives us our result. And because I've changed it to a float, I'll now show you what's happening on the screen. I've deleted the millivolt, so it's not going to show MV on the screen. It gets in the way of the result. I'll just build that for you. Right, so now this is what you get when you float the result. And that is actually our voltage, 3.254. But we don't want it to that many decimal places. Leave it like that for now. So I'm hoping that's more accurate than my power supply. So 3.3. 3 point. Turn it down. Well, you see I've turned it down to 3 volts. And we've got 3 volts there. So that's now measuring our power supply. Remember, you can't go above 3.6 volts on this Pic. Anyway, I hope this has been useful. Hopefully you've learned a little. Thank you very much.